Welcome to the last afternoon session of this conference. My name is Elio König. I work at the Max Planck Institute for Solid State Research in Stuttgart in Germany. And it's 2 p.m. sharp, and I lose my citizenship if we don't start early or on time. So first talk, Qiong Ma, Boston College, stage is yours.
Thank you. So let me start, as everyone else, by thanking the organizers for the invitation to this beautiful place and this very informative workshop for me. And every time I come to here, I come to UCSB, I don't want to go back to the cold Boston. Okay, so my talk is about quantum geometric control of material phases, and I hope at the end of the talk you know what I meant by quantum geometric control. So the story I would tell two stories which are close related, and the story is very simple. So I will introduce. Okay, during this workshop, I have learned a lot of interesting materials, and here I want to introduce another two materials. And these two materials, one has a special chirality, and the other has a layered antiferromagnet states. And can you find some similarity between these two materials? Why I want to put them together? Okay, I guess one similarity I see here is for chirality and this layered AFM states, they always come in two equivalent configurations, right? For chirality, it come as left-handed or right-handed. For the layered AFM, it has this configuration and this configuration. And they are very symmetric in terms of band structure and everything. They are energetically equivalent. And you can imagine, without doing anything during this material growth or phase formation, they must come in equal probability, right? They must be there must be domains. Okay, what I will show is circular Price light is very important and interesting. It can favor one over the other in both cases. And that's basically the story I will tell, and you can leave now. So, okay, let's focus on the first scenario first. Okay, so the chirality I will be talking about, because the chirality means different things in our community, right? The chirality here is really a special chirality in a crystalline solid. And here, it is a symmetry property. So basically, if a material system does not have any inversion symmetries or mirror symmetries, it has a definite chirality. Okay? And here is a very nice illustration from a News and Views. And you can see this chiral chain in a crystal with translational symmetry, and very much like these DNA molecules. And this is the chiral crystals. And these chiral crystals have become very interesting in our community. So a long time ago, people already know there is this optical activity, means it can absorb left-handed and right-handed lights differently and transmit them differently, etc., like the sugar molecules. The same optical activities occur in the chiral crystals. More recently, people realized the chiral crystals host this electronic topology, like the wire semimetals in the trim points. And those spatial wire semimetals can support this interesting quantized photocurrent response, which is a very rare example of quantized response in a metal, except this interesting that Professor Charlie Ken just told us yesterday. Okay, and in our field, there are many groups theoretically and experimentally working along these directions and to find interesting things about the chiral crystals. Okay, so as in the previous slide, what I want to say is we can control this chirality. Okay, but if you look at these chiral crystals, this chirality is determined by the chemical bonding, which is formed during this highly energetic chemical reaction process. And I don't think, as a physicist, we can easily change it. And as a physicist, however, we have our tool of synthesizing materials or material phases, which is emergence, the theme of this workshop, right? So there could be some chiral structures that can emerge emerge from interaction effects from interesting things, right? And indeed, okay, sorry, forgot to mention this. So for this topology and chirality, there is this very interesting, informative review paper from Professor Claudia Felser, if you are interested. Okay, so indeed, there is some emergent chirality people have thought about. One example is this chiral charge density wave. And it is first proposed in this transition metal ditractionide, titanium diselenide. Titanium diselenide is a layered compound, okay, and it has a charge density wave phase transition around 200 Kelvin, which has been known for a while, okay, and this this material has a threefold rotational symmetry about the z-axis, and the charge density modulation has three equivalent directions. It's a 3Q CDW phase. And people often believe these 3Q vectors are really equivalent, and the charge modulations are equivalent along the three directions. This chiral charge density wave means that the 3Q vectors are actually not equivalent. So you can see here, so at each plane at a particular z, so there is only one Q vector dominant in this charge modulation. And for the next plane, the dominant Q vector rotates, and it keeps rotating along the z-axis in a clockwise and counterclockwise way. That's how this chirality emerges in this density wave. Okay, and the first hint was in this STM measurement. But as you know, the STM measurement is really surface sensitive. However, this chirality is really a 3D bulk property. You have to go into the Z by a good amount in order to say it's chirality. And that's why there have been a lot of debates for this. And I hope our measurement can provide some extra hints on this. Nonetheless, during the past few years, this chiral charge density wave has been hinted in many other interesting material platforms, including this Kagome metal compounds, and also this quantum spin liquid compounds, and also others. So this is STM measurement, this is APAS measurement, and see these chiral structures. Okay, now what is our probe for this? I'm not doing STM, I'm not doing APAS, I'm doing optics. So, and our probe is actually a combination of optics and transport, is so-called photocurrent or optoelectronics. Particularly, we want to study an effect called circular photodynamic effect, meaning if I shine a circular polarized light, it can generate a current. Okay, usually the current in transport measurement is generated by applying some voltage, but here the current is really generated by the light, and we do not need to apply any voltage biasing or current bias. Okay, so and the CPG is unique that the chirality of the light determines the direction of the current. If I flip the chirality of the light, I flip the direction of the current. And moreover here, so you see this arrow of the current is along the same direction as the light propagation. That's not accidental, that's on purpose. We want to study this so-called longitudinal CPG. The current is along the same direction as the light. Okay, and why so? It's because after symmetry analysis, we find that this longitudinal CPG is uniquely linked to the special chirality of the material. It means if I measure this longitudinal CPG, it means this material I study has the special chirality. It's also true the other way around. If I have a material, I know it has chirality, it must have this longitudinal CPG. So we can check the second claim very easily because we have this chiral topological materials that people have already synthesized and measured with APAS. One compound is this cobalt silicide. It has a chiral structure. So we measure the CPG for both the transverse configurations and the longitudinal configurations. Just for people who are familiar with transport measurement, here the transverse means transverse to the light propagation, and longitudinal means means parallel to the light propagation. And what I measure here is the x-axis is the photon polarization, which is controlled by a quarter wave plate in our measurement very easily. Okay, so it's from it can change the light from left-handed to linear to right-handed to linear, so on and so forth. And for the y-axis, it's a DC foot current generated. It's a DC measurement. Okay, so for the first two cases, when we measure this transverse response, we do not see any modulation here, meaning, you know, first, the circular light did not produce a current, and second, there is no difference between the left-handed and right-handed. But here in the longitudinal configurations, we see this huge modulation. Compared to other compounds, this is very huge modulation. And moreover, you see here, which corresponds to the left light, and here corresponds to the right light, there is a huge difference. And in the ideal case, there must be equal magnitude and opposite, which is here. Okay, so for the real measurements on titanium diselenide, we will be looking at this kind of curve when we cool down this system. So this is the material. It's layered, and we have top electrode and bottom electrode. And top electrode is graphene, which is transparent, allowing the light coming in without much loss. Right? And we measure this vertical current, which is parallel to the normal light incidence. So we first measure this at high temperatures, and of course we do not see much. But at low temperatures, we do not see much. Okay, it's basically a negative result, and it's kind of disappointing. But okay, that's not the end of the story, obviously, and it's not that surprising if you think carefully, because as mentioned early on, if some chirality emerges in this system, it must be left-handed and right-handed domains, right, of equal probability. If the domain size is small, then our beam spot size, which here our beam spot is like 10 micrometers, so usually the domain is much smaller than that. So it's not surprising to expect that the signals averaged out by the domains of the opposite chirality. And intuitively, you can understand that the different chirality will give you the opposite photocurrents, and which will cancel with each other if we measure as a whole, right? Okay, so how to deal with this? So one way, obviously, if I can make our beam spots like nanometers, okay, that is very challenging. Only a couple of groups in the world can do this, and even they can do that. So a technical challenge is for the near field technique, which can break the diffraction limit, the polarization of the light cannot be maintained at the current stage. So it's basically impossible. So the other possibility is if you think about a ferromagnet, right? So the ferromagnet has been up, spin down, or and how to get a single domain? You use the magnetic field to train this material, right? During cooling, or at low temperature, you apply a large magnetic field. Okay, and the first, the field cool is usually more energy efficient. That's what we try here. So we starting from the high temperature, we cool down our material in the presence of the left-handed light. And this time immediately without doing anything. So we see this large modulation between left and right-handed lights, and it's very obvious. And then we warm it up. So you see it rapidly disappear around this charge density wave transition temperature. Okay, and we can warm it up again and train it with the opposite chirality, and at this time all the currents kind of flip side. Okay, and this can be reproduced many times on the same sample and also across many samples, and I show just another round. Okay, so yeah, so basically this picture intuitively we can understand it, right? So yeah, without the help of the light, these two domains are energetically degenerate, and with the light, you can make one lower energy than the other, and with the opposite light, when we make the other one favorable. The question is, what is the coupling? Okay, why these two chiral domains can couple the light differently and have different energies? Okay. That's the theory was proposed by our collaborator Di Xiao and his postdoc at that time. And so basically, yeah, so we need to find a coupling between this chiral light and some material property due to this chirality. And here is just one possibility. And the material property that Di found is this Barry curvature in this chiral phase. Okay, so it's particularly this dipolar distribution of the Barry curvature, the so-called Barry curvature dipole. So you can see these distributions are opposite between these two chiral phases. And this distribution, what does the Barry curvature dipole here do is that it leads to some optical activities. So the chiral domains can absorb the different lights differently. That's one possibility, one proposed mechanism. Okay, so from the experimental point of view, I want to highlight one thing, the importance of the photon energy. So here is the experimental systematic measurement with different photon energies. And you see that if you use a high photon energy around 1 eV, the training efficiency and the detection efficiencies are both very small, unless we go to very low photon energies as what we used for the previous data I show, which is the CO2 laser producing 10 micrometer light corresponding to 100 millieV. It's very large there. Okay, and this can even be reproduced in theory from the previous slide. And the intuitive way to understand this is, okay, this CDW has been measured by APAS, and this CDW gap is about 100 millieV. Okay, and this chiral phase must be related to these electrons. If we use very high photon energy to excite the high energy states, and they may not feel this this chirality. It's an emergent property. Okay, so I just want to broaden it a little bit to put this kind of measurement in the context. So this photocurrent measurement, so it's a nonlinear, it's a second order response because the excitation is at frequency omega, but the response is at DC, essentially 0, right? It's a second order response. Similar to this optical SSG, for which I think the previous speaker in the morning talked about the importance of these measurements, right? So actually they share the same kind of symmetry arguments, and they can detect the same symmetry properties of the material. To be complete, there is also this electrical version of the second harmonic generation, and a good example is this nonlinear Hall effect that I think another speaker talked about in the context of the wild condor system, right? The nonlinear Hall effect. And you think about it, it's really an electrical version of the SSG measurement. It's also sensitive if you can conveniently rotate the electrodes, you can map out the point group symmetry as well. And the importance to combine this together is, as you see, it can cover a broad wavelength range for excitation. And you all know that the excitation is very important for our studies because, they will be directly linked to the electronic states that we excite, right? If we want to study some emergent physics, some correlated states, some topology, we want the photon energy to be low, okay? And so by combining these three, so basically we will not need too much technical barrier, and many groups can do this. If you are interested in this, I want to shamelessly recommend to review articles. And during COVID and also waiting for my lab renovation, I don't have much to do and write to review articles and reflecting on this and sum up, I think, a good number of the most recent advancement in theory and experiment. But of course, it's far away from being complete, and it didn't include the interesting work that Professor Charlie Kahn talked about yesterday. Okay, so the second example. Okay, the second example. So the material I talk about is the manganese bismuth telluride. It's a layered magnet. Okay, it's a van der Waals material, and each van der Waals layer is actually 7 atomic layers. In between, it's a manganese layer carrying the local moments. Okay, and within each layer, the moments are aligned, and between adjacent layers, they are anti-aligned. And immediately, this gives rise to interesting layer-dependent magnetic properties. If we have odd number of layers, we will have a net moment, right? And people found it's a Qiong insulator. And if we have even number of layers, we do not have net moment, and people found it's an axion insulator. Okay, so we want to use circular polarized light to control this one. Okay, circular polarized light can control a ferromagnet with net magnetic moment. That's not a news. So we focus on this one. And how to understand the coupling between a circular light and the material. The most straightforward way is the so-called circular dichroism, meaning a material absorbs the left-handed and right-handed lights differently, and conveniently it is measured in reflection. It's all called reflection circular dichroism. So we just measure the reflection difference between these two lights. And this has already been done systematically, beautifully by Xiaodong Xu's group at Seattle. And they see this alternating phenomenon between even and odd layers around B equals 0. Okay? And that's not difficult to understand because, as I said, only the odd number of layers has the total magnetization, whereas the even number of layers that do not have the net magnetization. And normally people relate this, this circular dichroism with magnetism. Okay, so 6 layer and 8 layers do not have. Okay, then we need to think. So if some response is 0, and if we believe it's strictly 0, it means there must be some symmetry to prevent this from happening. Right? There must be some symmetry argument. And here, if we do the symmetry argument, we find that actually for both odd layer and even layers, the circular dichroism in the reflection channel should be allowed. Just to make it complete, actually their difference is in the transmission channel. So for magnetism, it has the CD in transmission channel as well, but for this even layer antiferromagnet, it cannot support it in the transmission channel. Then the question is why we did not see in the previous slide when we measure in the reflection channel. And it turns out the photon energy is the key, okay? And also, here you see the contrasting behavior between reflection and transmission. That motivated us to make this apparatus for our use. So in this setup, we can measure photon energy dependence, and we can also simultaneously measure reflection and transmission with magnetic field. Okay, now let me show you the photon energy, why photon energy is important. Okay, so the first, I show the excitation with the red laser. Okay, and you see the 5 layer has CD and hysteresis, but the 6th layer does not have CD. Okay, it's basically 0 at B equals 0. This is consistent with the previous slide. But things change if I use the infrared, near infrared laser here. So for 5 layer, we do not have CD. And for 6th layer, instead, we have the CD with the hysteresis. Okay, and this immediately means we should look at the spectrum. Okay, this is a 5-layer spectrum, and you see this modulation as function of photon energy, and also there are 2 zero crossings. And these two zero crossings are accidental. It's not enforced by any symmetry. It's just an accidental thing. Okay. And this is a 6-layer spectrum. And also, we have large response and modulations and zero crossings at a different wavelengths. So immediately you can understand why by using different wavelengths, sometimes we see this one is non-zero, this one is zero, and sometimes we see this one is non-zero, this one is zero, right? And it's consistent if you look at a 7-layer and 8-layer. Okay? And this means this circular light couples with the even layer through a distinct mechanism from the odd layer. Okay, and maybe more obvious contrast, as we mentioned, should be in the transmission channel. Okay, so here is the simultaneous measurement of the reflection and transmission. For 5-layer, you see this both in the reflection channel and also in the transmission channel. Right? But for 6-layer, you only see it in the reflection channel, not in the transmission channel. And this is the spectrum. Okay. This red curve is the transmission CD spectrum of the 6th-layer. And you can see the difference between accidental zeros and the zeros enforced by some symmetry. Okay, so now the question is, what is the mechanism? What is the mechanism for the circular light to couple with this AFM state? And this AFM state, which I did not mention, has a special PT symmetry. It's a parity times time reversal symmetry system. And this one is time reversal symmetry, but P is preserved. Okay, so I don't know whether Ashwin is in the audience. So the theory is proposed by Ashwin, and I hope that if hard theory questions, and Ashwin can help me. But yeah, so let me scratch the surface of the theory understanding. Okay, so for this even layered AFM state, 2 layers, 4 layers, or 6 layers, you see the top and bottom have opposite spin moments. Okay, it means it has opposite Barry curvatures between the top and the bottom. Okay, when the light comes in, let's think about the electric field in this light. Okay, if I have an electric field here, okay, then what it does is it induces the Hall current, opposite Hall current between the top and bottom surface. And essentially, it's a circulating current. And the circulating current will generate a magnetic field. And that is the optical magnetocoupling. And for the opposite AFM configurations, you have the opposite Barry curvature between the top and bottom, opposite configurations of the Barry curvature, and you have the opposite magnetization generated. Okay, so this mechanism tells you, the coupling with the circular polarized light by these two opposite AFM domains are opposite. It can induce some energy difference. So we apply this to control our AFM, to control it and to detect it. And the detection is through the CD. Okay, so if we measure a positive CD signal, it means we're in one of the AFM domain, and if we measure opposite CD signal, we're in the other. Okay, so we do it in the energetically friendly way by cooling the same training business as titanium selenide. So we cool down from 30 Kelvin to 2 Kelvin. The new temperature is about 20 Kelvin. So, and you see, we start to see the CD signal. If we train it with the right-handed light, sigma plus. If we train it with sigma minus, which is the left-handed light, we see the opposite CD signal. We can also, during cooling, we can use 2 beams of opposite chirality, and we can write this AFM domains like this. If at low temperatures, if we let the sample sit at low temperatures, we can use an ultra-fast, intense laser to switch the domain as well. Okay, with that, I want to thank all my collaborators, especially for the for the MBT work, it's led by Professor Suyang Xu and his student, and also theory was proposed by Ashwin and his postdoc. And all these people, I have been discussing about the nonlinear physics and the co-writers on the review papers. And with that, I'm happy to take any questions.
Beautiful talk.
In the first slide, you showed that if there was a current flowing, is there no voltage, or were you applying a voltage?
Here?
Yeah, when you see the actual effect, you said there's a current that flows when you put have a particular helicity for the photon.
Yeah, it's just the imagined circulating current. We're not measuring the current. We just measure this optical signals. We do not measure this current.
Oh, there's there's no current.
We do not measure it. It's just a way to help understanding.
You're just measuring the absorption. You're measuring the
yes,
differential
yes,
in the absorption of left and right circular polarity.
Yes,
so
yes,
MCD,
yes. Essentially,
it's a classic MCD effect.
Yes.
It's not a. Yeah, good.
Yeah, essentially.
For the cobalt silicide, you said that even without any training, you were able to see this chiral effect. So you think that the domains are pretty large in cobalt silicide?
Yeah.
Do you have an estimate?
Yeah. Well, so I think our collaborators did some X-ray on the structures, and they can see. I mean, sometimes a single crystal can be mostly one. I mean, we do not need this crystal to be 100% left-handed or right-handed. Let's say if 80%, 20%, we will see a signal. Yeah. Mm-hmm. So I forgot the exact number, but it can be largely one domain for a single crystal.
The other question that I have is, can you show those view graphs? It's for the latter compound where you have hysteresis curves, and they say, well, in one part of the cycle you have AFM1 and the other one is AFM2.
Mm-hmm. Yeah.
How does the system decide that if you start with a negative magnetic field, it will choose AFM domain 1, and then if you go positive enough, it will choose AFM domain 2?
You mean here? This curve?
Yes.
This curve. It's because there is a finite electric field. There is a axion field control of this AFM domain. It's a E times B control of this AFM.
Okay. I guess I'll ask you later.
Yeah.
Further questions?
Very nice talk, thank you. I'm curious, the wavelength dependence. So I'm supposed to be thinking about the effects as a Berry curvature effect, and so
one possibility.
So I'm not thinking about then calculating the Berry curvature of the ground state. I'm thinking about calculating Berry curvature of excited states of part of
yes,
of
exactly.
what the okay.
Yeah, it's not a Berry curvature at the Fermi surface. It's the Berry curvature at the energies that connected by the photon energy.
And you would integrate this, or
yes, we need to integrate it over this constant excitation energy contour.
Okay, thank you.
Further questions? Yeah. Magna was first.
So thanks for the nice talk. I wanted to understand, so the Berry curvature dipole in the excitation spectrum, so the Berry curvature usually transforms like a magnetic dipole. If you have a dipole of dipoles, that suggests thinking of it in terms of a quadrupole. So is there any, so this is of course not in the ground state, but in the excited state. So should you?
It's the same, it doesn't matter. So yeah, it's, the Berry curvature is like a magnetic field, right? It's like a magnetic field. And the Berry curvature dipole is just a derivative of the Berry curvature along X, Y, or Z.
So you're saying I should not think of it in terms of a magnetic quadrupole at all?
No.
Okay, all right, thanks.
Is there a minimal magnitude of the electric field for the training light?
For the we did not approach very low, I guess. So this is the photon energy dependence. So it's only test of like 4 points. It's linear.
No, for the training light.
This is a training light. Sorry, this is induction means training. It's the training light power.
And what electric field does it correspond to?
Oh, I cannot calculate it from the top of my head. This is a CW laser, though. The electric field shouldn't be high. Yeah, that's why we are not able to flip the domain when the temperature is low. Otherwise, we will not be able to measure it, right? We also use the superpolarized light to measure it. If the superpolarized light can flip the domains, we will not be able to measure it. But yeah.
But you also showed this ultra-fast flipping of the domain. And in that case, is the electric field much larger?
Much larger, because it's femtosecond laser pulse, and for average for similar average power, the peak intensity, the peak electric field is much higher than CW.
Okay, because I was wondering if you ever access the regime where Fouquet physics matters.
Fouquet physics.
Yeah.
Yeah, that's a good question, and
you probably need electric field of like 10 to the 8 volts per meter to access Fouquet physics.
I see. I don't think we're that high, and in fact, for the AFM domain manipulation, we still believe it's a thermal process. You know, the ultra-fast laser locally heated up and goes through this training locally, not globally. Yeah. We still think it's more likely to be a thermal process, but it will be more interesting if it's a non-thermal process.
You could imagine like you have Fouquet bands and you thermalize within this Fouquet band because you have relaxation also with Fouquet. I was wondering if I can think of your cooling process as this type of thermalization within Fouquet bands, but apparently it's not needed to think of it like that.
Yeah, we have a simpler explanation, but that is, I wonder what signatures can tell me that is the case.
Okay.
I can't talk about this.
So going back to a couple questions ago, the Berry curvature appears in some integral, you said. Presumably it's with some form factor?
Sorry?
The Berry curvature would appear, and you said it appears in an integral.
Integral,
yeah. So it's integrated with something, right?
Integrated over the case K.
Yeah, I guess what I'm wondering is, can you really like isolate the Berry curvature, or is it integrated with some unknown form factor?
Okay, it's integrate of the Berry curvature dipole. So the Berry curvature dipole is a derivative of Berry curvature relative to x, y, z. Yeah.
Other questions? Maybe I ask directly as a subsequent question to this. In your CDW material, this titanium diselenide, this is not a regime where you have an expectation for a quantized CPG, is it right? Or would there be something which is quantized, some trace or something?
Yeah, that's a very good point. As I mentioned, there is a very interesting connection between the spatial chirality and the electronic chirality, which is the wire nodes, right? If we can change the spatial chirality, we can change the chirality of the wire nodes. So in principle, we can do that. We can change the chirality of the wire nodes. But the first thing is we need to calculate. We need to really calculate the band structure in the charge density wave phase. The caveat is that we can only detect the symmetry. We know it's chiral. the chiral check density wave proposal, and we borrow this chiral CW proposal, right? So, and based on that proposal, we calculate the band structures, and we can, in principle, try to find that wild nodes. But that really depends on whether this chiral CW model is correct or not. Yeah, but that's a good direction. So we can, in principle, we can try to calculate the band structure and find the wild nodes and find within what photon energy range it stays as linear, and how large the energy separation between the two wild nodes at trim points. And if that energy scale is large, in principle, we should be able to see.
But as a function of photon frequency, I probably don't have experimental data yet for that, right? Do you see a plateau as a function of photon frequency?
Okay. We will not be able to see that in our measurement, because our measurement is steady state measurement, and the quantized CPG, what is quantized is the injection current, and you have to measure it in a time resolved way, which is not our measurement here. Yeah, we will not be able to see the plateau.
Well, okay, fine. Let's just discuss it.
Yeah.
Very good. Cool. More questions? Yeah.
Nice talk. So I have two questions. One is, could you remind me of kind of a domain size for your chiral CDW domain?
Yeah, we have no idea what the domain size is, but from the STM measurement, if you trust it, they see this Q vector intensity counterclockwise domain that's on the order of 10 nanometers. And
if, CDW distortion really chiral,
yeah.
If I do a very good X-ray diffraction measurement, I should see kind of a modulation along, C-axis, like out of plane. But as far as I aware, nobody reported, that kind of a modulation for titanium diselenide.
Yeah. So what is the beam spot size of the X-ray? Okay.
So do you have a kind of any, or maybe, resolution of X-ray diffraction wasn't good enough?
Okay. That's one. I don't know, because our beam spot is like 10 micrometers.
That's interesting to see that.
That's much bigger. That's supposed to be much bigger than the domain size, for sure. Yeah, but I'm always wondering whether in the X-ray facilities people can do this training with the light, or in STM people can do the training with light. Maybe it can help. Yeah, can see this domain change, can see the domain growth.
I see. Yeah. Good. Yeah, thank you.
You mentioned before that you were using a femtosecond laser to pump it? Or?
Yeah, for the magnetic system.
For the magnetic system. So did you then look at the relaxation dynamics as well?
No, not yet. Not yet. Yeah. Okay. We use the ultrafast laser just for its intense electric field, but we haven't done anything time resolved.
So what measurement did you then do exactly then? So you pulsed it with, you had a femtosecond pulse of circularly polarized light.
Yes.
And then what? And then you measured slowly afterwards, or?
No, we haven't measured as a function of time. We just use it the same way as we use the normal CDW laser. We shine it and then measure we shine the laser on top of the sample and remove the laser and measure the CD and measure the circular dichroism.
I see.
Yeah,
okay.
Because
so the domain forms that quickly. So within that few femtoseconds, you actually get you start with the sap which has no circular dichroism, and then so it instantly lines up. That's extremely fast.
We cannot say that because each pulse is femtosecond.
Right.
But in our measurement, there are many pulses coming in before we measure it. We just use the laser to shine on the sample for a while, like for 10 minutes. And during 10 minutes, many pulses come in.
And then the CD you measure at the end of the 10 minutes?
Yes.
Oh, okay,
yes.
so your nucleate, so we don't actually know anything
yeah.
about the nucleation and growth of these things.
Yeah. We just utilize the high intensity at the peak to melt this. That's what we believe. It's just to melt this order first and then let it develop under this circular light. It's the same as the training.
Okay.
Yeah.
Okay, very good. So unless there are extremely urgent questions, I propose that we just switch to the next speaker and thank Qiong Ma again.